Oh, hi there, everyone. I didn't see you there. It's so great to see you. You've all shown up for your learning, and that's fantastic. Today, we're going to be reviewing exponent laws to get ready for exponential functions. I'll talk more about how cool exponential functions are and where they show up in life a little later on. But for today, let's just review the math so that we can get this stuff under our belts as effectively as possible. So first of all, get some definitions around the power that I gave you. We're going to be looking at, I think I gave you, what was it, 3x to the 7? It's kind of that weird pixelated picture. It looks like it was, it's been censored or something. But it's not dirty, I assure you. Go ahead and we have 3x to the 7. We want to know that that's 7. We're going to call that an exponent. That's the number of times that we're going to multiply x by itself. X, this thing, is called the base. A 3 in this case is not being exposed to the exponent. That is just a coefficient. And then the whole thing taken together. Oh, I would actually consider this the whole thing. This is called a power. A power is like the exponent and the base together. If I say raise a power to a power, that means like I take that whole unit of stuff and raise it to another exponent, to another power. Okay, so that's just some definitions so that you know when I'm using those words, that's what we're talking about. We particularly want to know about like the idea of having the same base for these types of laws. And that will be a mistake that people might make is applying these laws when we don't have the same base. You have to have the same base to use these laws. What are the laws? Let's take a look. So the first one is a multiplication law, or I call it the product of powers law. Product's another word for the result of multiplication, and we're multiplying two powers together. So product of powers law, I like that because it's alliterative and it's easier to make poetry out of. So when you do that, you want to make sure to know that you add the exponents. When you have something like x to the 2 times x to the 3, that's equal to x to the 2 plus 3. So you might want some examples like that written down in the handy dandy chart, which I provided you for your studying purposes. Yeah. And when you're thinking about an algebraic model for this, an algebraic model would be one that you could apply anywhere. So then we could say, if I have x raised to the power a, and I multiply that power by x to the power b, what will that give me?
AB.
X to the, I'm still waiting for the correct answer. The a plus b.
That goes in the algebra box.
Yeah, I would put that in the algebra box so that I have a model to study from. So we add the exponents when we're multiplying when we're multiplying powers that have the same base, you add the exponents together. Now, anyone feel like oh wait, we have to do this to Caitlin. See how effective that is? It's really effective. So you probably feel like, oh, I remember learning that and I forgot. And that's fine. I'm going to teach you how, just like a mathematician would, you can forget stuff like this all the time, but then reteach yourself even in the middle of the test. Let's say I have something like this and I don't know what to do with it. Well, I can say x squared. I can write that as multiplication like this. And then x to the 3, I can write that as multiplication like this. And then it's just so clear to me that I have x multiplied by itself 5 times. So that's x to the 5. This is proving the rule to yourself through multiplication. Exponents are weird. You've been multiplying things since grade 2. So take this more complex thing and see it in a simpler way to remind yourself. That's called, I have x times itself 1, 2, 3, 4, 5 times. Oh, I can see however many times I'm multiplying there, however many times I'm multiplying there. Just add them together, and that's how many total times I'll multiply. So that's why this rule works with multiplication, to show you. Carry on. Let's go. Oh, you can also use this for mental math. If you have something like 4 times 16, you could think of that as 4 to the 1 times 4 to the 2 and see that that will give you 4 to the 3 or 64. Okay? Or you could have even seen that as 2 to the 2 multiplied by 2 to the 4. That's another way of writing 4 times 16. And then you add the exponents, 2 to the 6. 2 to the 6 is 64. So you can use this for mental math as well. I do it all the time. Simplifies your work immensely. So let's keep going. Division law, or quotient of powers law. Quotient of powers rule is what I call it there. When you're dividing, you do the opposite of when you're multiplying, you subtract. Okay? There's a nice symmetry to this. I think you'll agree. Multiplication is the opposite of division. Addition is the opposite of subtraction. So isn't it neat that when we were multiplying, we added, and when we're dividing, we subtract? There's a kind of symmetry there. Now let's take a look at what that means. If I have x to the 5 divided by x to the 3, well, that's x to the 2, but it's also, you can write it as x to the 5 minus 3, which is 2. It's another way you can have that intermediate step in there. An algebraic model would be x to the a divided by x to the b. What will that be? Excellent, x to the a minus b. And I would encourage you to write brackets around your exponents there. That will help you communicate with your calculator, and that will help you communicate with your reader, and it will help you avoid errors. Okay, just put the brackets around the a minus b. Strictly speaking, they're not required. If both the a and the b are in superscript, that means they're both exponents. We should imagine brackets around them anyway, but drawing the brackets just helps you be really clear. Now, let's use multiplication to prove this to ourselves. Take this example, x to the 5 divided by x to the 3, and write it out with multiplication. X times x times x times x times x. That's x to the 5, all divided by x times x times x. That's x to the 3. And then we get to get out our cancel pen. So exciting. X divided by x is just 1. X divided by x is just 1. X divided by x is just 1. So this is the same thing as saying 1 times 1 times 1 times x times x. So we have x times x twice, it's x squared. We can see the subtraction happening through the cancellation that division provides us. So that can, when you invariably forget this, you reteach yourself. And when you have that ability, you don't need Google all the time. You understand the process that much better every time you forget it. The number of times I've forgotten this stuff and retaught myself, many times. So I have a good understanding of it at that level. All right. And again, you can use this with mental math situations. If I have something like 48 divided by, let's go with 32. Okay. I see these as products of primes. So 48 is 3 times 16, which is 2 to the 4. And 32 is just 2 to the 5. So this is equal to 3 multiplied by 2 to the 4 minus 5. That's going to be 2 to the negative 1. It's going to lead us to another slide a little bit later down. But you can also notice that that's just 3 over 2. Okay, and that's the answer for 48 over 32. Let's keep going. Power to a power law. All right, this is when you have a situation like this where you're raising one power to another exponent. In this case, you're going to multiply the exponents together. Let's get ourselves an algebraic example. X to the a to the b. X to the a brackets raised to the power b. What's that going to be? X to the ab, yeah. X to the AB. I need more rap lyrics for that cool little soundbite. Someone can come up with it. Maybe not me. I got other things. But that's your model there. Just multiply the exponents. AB means A times B. So there you go. Again, if you write this one out, this is 8x to the 8, which is x to the 2 dot 4. That's multiply. Okay, that's x to the 8. And let's use multiplication to prove it to ourselves. So this is x squared, right? And then I multiply that thing by itself 4 times. See why we multiply them? You see how you can do that yourself when you forget this rule. Just plan on forgetting it because it's a great learning opportunity. Oh, I forget this one. Let's see if, like a mathematician, I can reteach myself and reprove those ideas. Now, how about this one? Well, this one seemed like both things changed. Okay, let's take a look. If I break this one down, I'm going to use blue here and break this one down. What I do when I'm working with this exponent here, and again, with these exponent problems, you're going to work in Bedmas order. So we're going to resolve anything inside the brackets that we can. There's nothing to be resolved here. And then I'm going to do external exponents first, and then internal exponents. Like I'm going to bring that exponent of an exponent, do that first. So here, I can write this as 2 to the 5, x to the 2 times 5. No problem. 2 to the 5 happens to be 32. And here, the counting on your fingers trick is really useful for your powers 2, your powers 3, and it's a great math workout. 2, 4, 8, 16, 32. That's the fifth bone that I've counted. So 2 to the 5 is 32. And then I could go 64, 128, 256, etc., 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 etc. So you can count your powers and just keep track that way, like your fingers are an abacus. Let's keep going. So this is 32x to the 10. Questions about power of a power law? Well, let's keep going. What if we have a 0 exponent? It's always 1. Okay? And this wants to start making sense intuitively. X to the 0 is like saying, I have some number that I don't know yet, and I want you to multiply by that number exactly 0 times. Meaning, please don't multiply by that number. Please just leave the random multiplication placeholder as 1. The multiplication placeholder is 1. X to the 1 means 1 times x. X to the 2 means 1 times x times x. 1 is always there, but I don't usually show it. Okay, I am 1 times 42 years old, but I don't show that 1. It's there. Oh yeah.
Is that supposed to be 2x?
Where? Oh, x to the 2?
Yeah.
It actually doesn't even matter what it is. It could be 2x, it could be x to the 2, it could be x to the 57 bajillion chameleon. But still, because I'm raising it to that external exponent 0, this one here, its value will be 0. Okay? So you have this x to the 0 equals 1, but there's an exclusion there. There's a limitation. X cannot be 0. 0 to the 0 is actually the subject of some debate. And you don't need to worry about it. It will not show up on tests. It will not show up in your application problems. Okay? Don't worry about 0 to the 0. Leave that to the hardcore mathematicians to argue about. I should put it on the test. Maybe as a bonus. Yeah. Oops, what am I doing there? Showing you all my windows. Okay, so how would you prove this to yourself through multiplication? Let's examine this situation. X squared divided by x squared. What's that? That's 1, because it's something divided by itself, so that's 1. But it's also equal to x to the, subtract the exponents, 2 minus 2. 2 minus 2 happens to be 0. This is x to the 0, and x to the 0 is 1. So you can use other exponent laws to prove this one. Make sense? Cool. Cool. Let's go. Carry on? Carry on. Yeah, and you already have, this would be your algebraic model here. Like x to the 0 is 1, but x is not 0. It should have this restriction, and then it's robust. Then it's fine. Negative exponent laws. We are going to start getting very comfortable with negative exponents. You're going to see a lot of them. In a lot of cases, it's like project time backwards. We're going to see cases where time is the exponent, and so as time goes forward, things grow exponentially. If you wanted to not forecast the future, but examine the past and what was likely to have been, then you would use negative exponents for negative time. So let's take a look. How do we deal with negative exponents? When an exponential term has a negative exponent, you just flip it. It's just the reciprocal of that thing with the positive exponent. All right. So here is your algebraic model. X to the negative a is equal to 1 over x to the a. Just throw that thing to the bottom of the fraction and be happy. It's just there. There's another one. I'm going to write this one out. I shouldn't have to, but I'm going to write it out anyway. No, I should have to because some of you won't know this. 1 over x to the negative a will be equal to x to the a. Flip it. You don't need to throw it to the bottom of yet another fraction because then you would be dividing by a fraction. You would flip and multiply anyway, so just flip it. Okay? So if you ever see a negative exponent, just flip that thing off. And then you've resolved it. All right, so in delta math won't like negative exponents. And it will tell me the answer with positive exponents only. So if you get to something like x to the minus 3, it wants you to express it that way. If you get something like this, it wants you to express it that way. Now, why is this happening? Let's take a look at an example. If I had x squared over x to the 5, and I wanted to know what that is, you might be able to see that if I expand this with multiplication, I'm going to end up with 3 uncanceled x's on the bottom. This cancels that cancels that, and 3 uncanceled x's still exist on the bottom. This is 1 over x to the 3. If I used my quotient of powers law or my division law, I would have this as equal to x to the 2 minus 5. My son, he's 4, he's obsessed with negative numbers right now, and he follows me around with a calculator doing calculations, and he says things like, is 89 minus 100 negative 11? And I say, yes. So 2 minus 5 is indeed x to the minus 3. X to the minus 3 is the same thing as saying 1 over x to the 3. Okay. So if you forget, what do I do with this negative exponent? You can use your quotient law to prove it to yourself. Okay? I give you permission to forget this stuff, but I do not give you permission to ever feel helpless about it. Okay, there you go. Okay, let's keep going. Let's look at some examples. How are we going to use this? Well, here's an example. We're going to solve it in Bedmas order. Let's go. This one goes like this. Well, I'm going to have to resolve this exponent first. Let's do that first. I cannot go ahead and cancel in here, like saying y to the 5 and y to the 5 cancel each other yet. Sorry? Nine x to the power of 8 and y to the power 10. Yes. Yeah. So let's take a look at that. I can't do this cancellation in there yet because Bedmas. So I have to resolve this bracket and this external exponent first. So that's going to be 3 squared x to the 4 times 2, y to the 5 times 2, all divided by x to the 2, y to the 5. Simplify. 3 squared is 9. X to the 4 times 2 is x to the 8. And y to the 5 times 2 is y to the 10. All over x squared y to the 5. And then we use our quotient of Powers' law to say, well, this is 9, x to the 8 minus 2, y to the 10 minus 5. Feel free to skip any steps that you need to skip to streamline your work. 9x to the 6, y to the 5. Just like that. Give me a thumbs up when I should continue. Wait for a couple more. Cool. All right. I appreciate I didn't give you that much space for the next couple examples, but we'll see. Okay, let's keep going. So, if we want to simplify these using exponent laws, all right, well, let's see if we can simplify that 25 over 5. We can write that as 5 squared over 5. Those are our numbers. X to the 5 minus 5, y to the 6 minus 8. 5 squared? Oh, 25.
Oh, I see.
I just wrote it as 5 squared so that I can use my exponent laws. Okay. Then this is 5 to the 1, right? Because everything is to the 1. I'm 42 to the 1 years old. And then I can express this as, instead of 5 to the 1 on the bottom, let's cancel that and make this 2 minus 1 up there. So I use my quotient to powers law to simplify this fully as 5 to the 2 minus 1 is just 5 to the 1 is 5. Okay, that's a long way of doing this division, right? 25 divided by 5 is 5. No problem. It's just equal 5. X to the 5 minus 5 is x to the 0. Oh, that's 1. It's not 0, it's 1. And then y to the 6 minus 8, so it's y to the negative 2. Oh, I didn't want to write that with a negative exponent. It's 5 over y squared. Done.
So in the x disappears. It's 5.
Yeah, it's 5x over x to the 5 over x to the 5. It's just 1. So those canceled out. They still would give me a restriction though. X can't be 0.
Could you also write that like 1 over 5y2 or
1 over.
5y plus 2 or no?
No, because the 5 has to be on the top.
Oh, right. So it's multiplying 5.
Yeah. So with addition and subtraction, they're basically the same thing, but numbers are either positive or negative, and then I smash them together. And that's addition and subtraction as one operation. Division and multiplication can be similarly thought of as it's the same thing. I'm multiplying together, but things are either on the top of the fraction or the bottom of the fraction. And in this case, the 5 lands on the top of the fraction. It can't move to the bottom of the fraction. I could write it in this way, Caden, but that would be really awkward. 5 to the negative 1 on the bottom. 5 to the negative 1 y squared.
Could you have 5 on the outside though? Like 5 multiplied by 1 over y?
Ugly. Sorry?
Could you have like 5 multiplied by?
Yeah, I could do it this way. 5 multiplied by 1 over y squared.
That's what I've seen.
Yeah, but that's the same thing as writing this. They're all the same way of writing the same thing. To me, this is the tidiest one.
Yeah.
That's the tidiest one. That one gets the math smiley face.
5 over y squared.
5 over y squared is my preferred form. The rest are ugly to me. Okay, let's keep going. Thumbs up. Yeah. I'm going to do this example, and then I feel that I need to add another example because I want to talk about when your base is a fraction. When your base is a fraction, I want to talk about. There's no new rules for when your base is a fraction. You just apply your knowledge of fractions. But let's take a look at this one first. Okay, this one, we have to resolve this exponent first, and we can also do this multiplication in here as well. So let's go. The 5 is going to raise all those things to the power 5. So that's going to be 2 to the power 5, x to the power 5 times 5, or x to the 25. See how I'm skipping steps already. And y to the 25, that's 5 times 5, using my power of a power law. And on the bottom, I'm going to have negative 6, but I'm going to write negative 6 in a new way. Negative 3 multiplied by 2. That's negative 6. What?
Why would you do that?
What? Why?
No, like why?
Well, because 3 times 2 is 6,
Yeah.
but it's negative, so that's negative 6.
Yeah. Why would you do that though?
Just
add one variable.
Because I'm a math dude. Doesn't add more variables. You'll see it simplifies things. X squared times x to the 3 is x to the 2 plus 3. It's x to the 5. And y to the 4 times y to the 5 is y to the 9. All right? This 2 is 2 to the 1. It's going to cancel one of these 2's in the top.
Oh, because it's
Yeah.
multiplying.
Yeah. So this is going to be equal to 2 to the 5 minus 1 on top, or 2 to the 4. See why I did that now?
No. Wait. Oh, wait. What? Oh.
I noticed that 6 contains a factor 2.
Yeah.
I notice these things because I'm highly trained in the arts of mathematics, and I remember facts like 2 times 3 is 6. Sorry, I'm just embracing my inner condescension. Sorry, I apologize for that. I know you all know that 2 times 3 is 6, but I write it that way so that I can cancel and use my exponent laws to simplify things a little faster. And then I know that the 3 is going to be left on the bottom. So 3 is on the bottom, it's still negative. Okay, I've resolved this 2 already. Its job was to take away one of those 2's and make that a 4. Okay? And then I have x to the 25 on top and x to the 5 on the bottom. So I'm left with x to the 20. Y to the 25 on the top, y to the 9 on the bottom. So I'm left with y to the 16. And this could be my final answer, but I can simplify this a little more and tidy it up. 2 to the 4, I don't feel like checking my calculator, so I do this. 2, 4, 8, 16. Okay, it's 16. All right, so that's equal to negative 16 x to the 20, y to the 16 over 3.
Well, he just moved the negative from the 3 after.
Because writing the negative on the bottom of the fraction doesn't earn the math smiley face. It's ugly. Okay?
How did that switch to 16 now?
When you turn that to 8.
Well, it's 2 to the 4 is 16.
Oh, sorry.
I did some counting on my fingers and found that if I multiplied by 2 4 times, I got 16.
2, 4. Wait, 2.
Does that turn into 8?
There you go. Yeah. Huh?
Does that turn into negative 8?
No, because it's 16 over 3.
Sorry. No. Oh, 16.
16 over 3, they don't share factors, so I leave it in this fractional form. If I want, I can express that as 5 1/3, but it's negative.
I was just trying to.
Or 5.3 repeating, but it's negative. But those are all, none of those earn the math smiley face from me.
Technically, you could. For a second, I thought
Yeah.
16.
This is math smiley face form.
In the math vibration, yeah.
Livia?
Could you slow down a little more, show more steps?
Yeah, can you show all the steps? All the steps possible.
All the steps
All
possible?
the steps possible.
Yeah.
Don't mind if I do.
Could you do it where you don't
Yeah, don't see the steps.
don't do the -3? Like, yeah, that's the only thing that makes sense.
Show all the steps. Baby steps. Like ripping it.
All right, let's go.
Alright. Let's see.
So we have, I'm going to bring this exponent in. It affects that term, and that term. Let's explore why. If I had 2x squared raised to the power 3, because that's about what I have the appetite to write out, this would be 2x squared times 2x squared times 2x squared. See how the number and the power are getting cubed. So it's 2 times 2 times 2 times x to the 6 in that case. Okay? So I'm going to use this logic. I don't have the patience to write that out 5 times though. I'm just going to use exponent laws. So what I'm going to have is 2 to the 5, x to the 5 times 5, y to the 5 times 5 when I resolve this exponent. Okay. And then I divide by, well, let's just work it out. -6. X squared times x to the 3 is x to the 2 plus 3. Y to the 4 plus 5. Erase my example. All right. So now let's work out those. This is equal to 2 to the 5. Do you want me to work that out, or do you want to leave it as 2 to the 5? You can do it either way. Would your instinct be to evaluate that or to leave it as 2 to the 5? Evaluate it? Sure. It's 32. X to the 5 times 5. 5 times 5 is 25. Y to the 5 times 5. 5 times 5 is 25. Divided by -6. Note at any time I would be floating this negative up to the top. I don't like negatives on the bottom of fractions. I float them to the top. It's the same. A over -b equals -a over b. There's no algebraic doohickeys to worry about. -a over b is all the same. All are the same. This is my preference. This is also fine. Doesn't bother me one bit. This is a maniac is doing the math. Someone needs to talk to that person. Okay. And then we have x to the 2 plus 3. That's x to the 5. 2 plus 3 is 5. And y to the 4 plus 5 is y to the 9. All right. So that's how I got to my first step. I just assumed the product of power laws and then the power of a power laws there.
Alright.
Okay, now 32 over 6, I notice they both are divisible by 2, so I divide that factor 2 out. Okay, same as the way I did it, it's just a little bit different. So this is 16 over 3, but it's negative. I cannot bring myself to write that as negative 3 anymore. Please allow me to float the negative to the top.
Where's the 2 go? Doesn't do it.
What 2? The 2 over 2?
Yeah.
2 over 2 happens to be 1.
Yeah.
I'm 42 multiplied by 1 years old.
Oh, that's good.
Yeah, so I don't show it. It
Oh, so
goes
it's equal-
off
so it's
into
equal to
the
0.
field of things we don't usually show.
So equal to 0. Right?
It's not equal to 0, it's equal to 1. Multiply by 1 is the same as doesn't change. Yeah. And add 0 is the same. Like I don't show that I'm adding 0 to all the stuff and that I'm raising everything to the power 1 and that and et cetera, right? There's a whole bunch of them that don't usually get shown. And then x to the 25 over x to the 5 is x to the 25 minus 5. And y to the 25 over y to the 9 is y to the 25 minus 9. And then we're ready to push this problem across the finish line. This is equal to negative 16 over 3 multiplied by x to the 20, y to the 16. Notice if I do this, it doesn't change. It's the same. Those things are on the top of the fraction. Olivia?
How did the 16 become negative 16? You just like take it from 3
Yeah.
and just
Because a over negative b is super ugly.
oh, right.
Stop writing that. Write it as negative a over b. It's identical. 2 over negative 3 is the same thing as negative 2 over 3. But negative 2 over 3 doesn't make me want to grab the garbage can, take it into the hallway, and retch. Cool. All right. So you're probably like, Mr. Jennings, you promised me one extra example. Let's take a look at the homework questions. Here's the homework questions. And I'm going to grab one of them and do one of them before your very eyes. So go ahead to 166 in your textbooks. Actually, it's 167. You're going to look at question number 7, which looks like this one in here, and I'll take a look at 7D. I think it's up on the board already, but I'll show you anyway. 7D. Here is the question. 4a cubed divided by 3b squared, all raised to the power negative 3. You may want this in your notes somewhere. So, there's a few ways to do this. Do you want to see the easy way or the hard way?
Just shove up.
Okay, I'll show you the easy way first. The easy way is, oh, I have a negative exponent. Those are annoying. Let's get rid of the negative exponent. I remember this. X to the negative a is equal to 1 over x to the a. Okay? If x is a fraction, let's say x over y to the negative a, well, that would be equal to y over x to the a, which would be equal to y to the a over x to the a. Just expand your power of a power law. So here you go. We're going to take away that negative exponent. It's now 3. And inside, I'm going to have 3b squared over 4a cubed. It just flips a fraction, folks. That's what a negative exponent does, is it flips your base.
The reciprocal.
It's the reciprocal.
It's like with slopes and stuff. You just put it upside down.
Yeah, you just put it upside down, whatever it happens to be. The reciprocal of 2/3 is 3 halves. Okay, so the reciprocal of that junk is that junk. Okay. So now we apply our power of a power law, but we apply it to the numerator and denominator because they're fairly ambivalent about multiplication. You multiply a fraction a over b times a over b, it's a squared over b squared. Leah?
9b.
How does it make sense that they're the same thing? Like the reciprocal. Like I understand that they are, but I don't.
Well, the reciprocal is not the same as itself, but if you have like x to the negative a, Well, this negative exponent tells you I want the reciprocal of x. I want you to throw x to the bottom of a fraction. Let's suppose we didn't know that x over y, its reciprocal was y over x. What I would do, let's say I have x over y to the negative 1. I would say that's equal to 1 over x over y. But then I just flip and multiply the bottom because I'm good at doing fractions. Y over x. Multiplied by 1. Okay? When you divide by a fraction, you flip and multiply. Right? Yeah? To make the exponent positive. So now we have resolved the negativeness of that exponent. I just flip it, and now let's evaluate it. This is going to be 3 cubed multiplied by b to the 2 times 3, all divided by 4 cubed multiplied by a to the 3 times 3. Okay? Power of a power law applied to the numerator and denominator. And then you just evaluate. 3 to the 3 is 27, and 4 to the 3 is 64. B to the 2 times 3 is b to the 6. A to the 3 times 3 is a to the 9. Done.
Wait, where did you get 27 from?
3 to the 3.
Oh.
3, 9, 27, 81. Keep going.
Wait, wouldn't it be a to the? Wouldn't it be 3 to the? 3 times 3? It's not.
No. The meaning of exponent is multiply that thing by itself 3 times, not multiply it by 3.
Yeah. Hopping for the b. It's like isn't the same thing?
B to the 2, yeah. So that's b to the 2 multiplied by itself 3 times. That's b to the 6. Power of a power law.
I thought it would have been like to the power of 3.
Like 2 to the power 3?
Yeah.
Like it would be to the 8? No. Because it's power of a power law. B squared times b squared times b squared is 2 plus 2 plus 2 is 6. But I don't use 2 plus 2 plus 2. I use multiply the exponents.
It never does that.
You know, you're never raising an exponent to an exponent unless you're doing towers of numbers. Those are called heavenly numbers. They get big fast. And they don't show up in our curriculum. So you're never raising an exponent to an exponent in our curriculum. But you can do that.
So that's like going like 3 times 3 times 3 times 3.
No, that's like, yeah, this is, like, let's write it out. So b squared to the 3, that's equal to b squared times b squared times b squared.
Yeah.
B to the 6.
Yeah.
Yeah, not b to the 8. Not b to the 8. You do not raise the 2 to the power 3.
Okay, that's what I expected. I guess I just had it.
That can be done, and it's called like either tetration or heavenly numbers. Yeah. Like if you have 2 raised to the power 2, which is raised to the power 2, which is raised to the power 2. See how these are going to heaven? And they get super big, super fast. And you don't need to worry about that in our curriculum.
Is that like next year?
No.
Not even?
No, that's like nerdy math stuff. Let's explore stuff that doesn't really apply to nature very much.
Is that what math is? Is that what our curriculum is based over? If you can apply some teaching?
Not necessarily. It's to prepare you for university level study, which is,
Isn't everything in preparation for something?
well, yeah, but it's preparing you to do practical things in the world, right?
When is it all?
All of this is highly practical. Towers of numbers, I struggle to find a practical application of it, but I find it super cool and interesting.
What's the most practical thing? Actually, that's a story. What's the most practical thing in math?
1 plus 2.
Absolutely. Livia, did you see enough steps?
Yes.
Yeah, okay. How is this fraction example?
That's gorgeous.
It's okay now? Like you can see, when I have fractions, I can use that and just flip it, and then I apply this exponent to the top and the bottom. And if you were confused, you could look at an example like x over y squared would be equal to x over y times x over y. You get x squared over y squared.
Does that
No, because they're not the same base, so we can't apply any more laws. Excellent question. Don't do that. Don't say that it's equal to 1, because x and y are different. We still have to evaluate. If x equaled y, then it would be equal to 1. But we don't know that. but not necessarily. We called them different letters. They're probably different things. They're probably a function. Okay, so I'm going to call this the video here and wrap it up. That was a long lesson. My goodness, thank you for your patience, everybody.
I actually understand it.